This interactive simulation looks at a plug flow reactor with a gas phase reaction where the number of moles increases. So this is looking at the reaction of A reacting to 2B plus C. So 1 mole going to 3 moles. And why this matters is then the mass density is going to change as we move down the reactor. Well, this has a couple effects. This means the volumetric flow rate, the velocity moving through the reactor changes, so there's less residence time in the reactor than there would be if the mass density did not change. The other way of looking at it is we have more moles, so the concentration of reactant is decreasing faster than just because reaction is taking place and we have less moles of A. In this particular case, we're looking at an extreme to make it easier to visualize. So we're looking at a second order reaction. And so as we lower the concentration, the rate goes down significantly. And we're looking at this big mole change. And what the simulation allows you to do is compare conversion as a function of reactor volume for the case where there's a density change, the blue line. And then the simulation also says, suppose we ignore the density change in our calculation. In other words, suppose we do the calculation as if the reaction was A goes to C. Well, that's what the dashed green line is. And so, for example, I'm showing here, you can see at the same, or essentially the same conversion, about 48%, the reactor volume is 20. So it's the value we can read up here. That's what we have control over. The reactor volume is 20. If we ignore the density change, and it's a much larger reactor if we take into account the density change, which is important to take into account. And so what the simulation allows you to do is change the temperature, which change the rate constants, which change how big the reactor is going to be. And then we can compare either at the same conversion, which I'm doing here, or by using the sliders for the volumes, I can compare at the same volume and see how much difference there is in conversion. And so we'll do that when we look at the interactive simulation. The other control we have is we can change the feed volumetric flow rate. So let's look at this interactive simulation, observe the behavior. So here we're looking at the interactive simulation, and so I can, for example, for these conditions, change the volume, and you notice if I want to get to the exact same volume, the easiest way is to go here and type in the value. So now, and I can then close that. So now I'm comparing at the same reactor volumes. If we ignore this mass density change, you can see we would have a much higher conversion than we actually would have in the reactor. And so this difference, of course, is going to get bigger. And so let's compare, and let's make the reactor bigger. So now we're comparing at higher conversions. Compare at higher conversions, there's a bigger difference, and maybe it's even more dramatic if I compare the volumes. And so if I want to move the slider slower, what I can do is hold down the control button while I select this, and then I can move this until I have the same density, 58% conversion. And now look at the difference in reactor volume. It's a factor of 3. So as we go to higher conversions, this difference in reactor volume becomes even more dramatic. And then the simulation allows us to change the feed volumetric flow rate, which of course affects the conversion. The reactant feed concentration, this is a second order reaction, so the reactant feed concentration is going to affect conversion. And then reactor temperature, of course, increases the rate constant, and so the conversion increases. And if we want to now compare at the same conversion, and I can do that by lowering this volume. So they're about the same conversion. Now notice there's more than a factor of 4 difference in the reactor volume, with density change included, density change not included. So in a plug flow reactor where you have a mold change, high order reaction can make a significant difference taking into account this mass density change as we move through the reactor.